In this pre-calculus algebra video, we will be looking at the polynomial functions and their graphs. At the end of this section, you'll see an example that explores how volatile gas prices have been over the past several years. And what's really interesting about this is that this question, the statement, was written even before our current state of gas prices just soaring. But you could imagine if you had a graph, if we had a graph of gas prices, we're not going to have an arrow, right? Because at some point at some date, there was a low point, right? We started somewhere. But the prices go up, come down a little, go up, come down, go up, etc. Right now, we probably feel like, oh, it's going way up. Is it going to keep going? Probably not, right? At some point, I have hope it's going to come back down again. But that's an example of a graph of what we'd call a polynomial function. Let's look at some examples of some of the things we can do with a polynomial function. It's important that you read the section in your textbook and pull out some of the key terms, definitions. But when we talk about what is a polynomial function, it is true that the exponents of the variables in a polynomial function have to be non-negative. We can't have a example like this where x is to the negative 3, because that would mean that it's now not polynomial but rational. However, the coefficient, this number in front of the x term, can be positive or negative. So the coefficients of the variables in a polynomial must be non-negative. No, that's false. We can have negative coefficients. And the graph of a polynomial function may have a gap or a break. That's false also. And let's think about that for a minute. We've been talking a lot about domain. Domain had to do with what values of x are allowed, right? And whenever we had a polynomial, it didn't even matter what the a and b, the coefficients were. Sorry, that's not intended to be a negative there. Here's an example of a polynomial, a general polynomial where we don't know the coefficients. But the domain of this, what x's are allowed, the domain of a polynomial function is always all real numbers, right? So what that tells us is that there are no gaps, no breaks. It's not like a rational function where we'd get an asymptote that the function doesn't cross, or a break in the domain where the graph of the function has a hole or doesn't ever cross. So for number 2, we have a false statement. The graph of a polynomial function may not have a gap that we can use to graph a polynomial function. The first one is this lead coefficient test. Let's talk for just a minute about the lead coefficient test. What we're going to do is put a polynomial in descending order. That means that the first term is the term with the highest n. In this case, to the right, we've got a 3x cubed. That's our highest exponent. So we'd say that the degree of this polynomial is 3. And because the degree is 3, what we're concerned about that 3 is that 3 is odd. So we have an odd degree. And when we look at the coefficient is 5, and that coefficient is positive. So when we have a term at the very front that's positive, and we have a degree that's odd, we're going to use the part 1, the part to the left, for the lead coefficient test. So here's what we do for the lead coefficient. Pull out the lead term, the 5x cubed. This tells me, this 5x cubed tells me about the end behavior of the graph. When you think about it, there's 4 possibilities, because to the left, as x approaches negative infinity, we could go down or we could go up. To the right, we could go, when you look to the far right, we could either, so in other words, as n, or as x rather, I'm sorry, as x approaches infinity, we could be going down or we could be going up. So that's what the end behavior is. At the end, to the far left, is the graph moving downward or is the graph moving upward? If n, the degree, so this 3, if the degree is odd, then it behaves like a cube function. If you think of f of x equals x cubed, and you can picture its graph, which I hope you can do that, it looks like this, right? F of x equals x cubed, the end behavior to the far left, it's going downward, to the far right, it's going upward. Now, if I did f of x equals the opposite of x cubed, now we're going to flip that, and to the left, we're going up, and to the right, we're going down. Now, what we have here, this 5x cubed, is like the positive x cubed. F of x equals x cubed. So this is going to behave, the end behavior will behave in the same way we see here. So when we use the end behavior, what we'd say is that this graph falls to the left and it rises to the right. It falls to the left and rises to the right. And that's the end behavior. Look at a few more examples of that and practice that. Make sure you're comfortable with the end behavior. Let's try another example here. If f of x equals the opposite of x squared times x minus 1 times x plus 3, and we want to look at the lead term, we can't just use the x squared, because if we were to multiply this all out, and I'm not going to multiply the whole thing, you could if you wanted to. We could distribute the x minus 1, x plus 3, and then distribute the negative x squared. But when I do that, do you see that we're going to have a degree of 2, and then 1 more, and then 1 more? So the degree will be 4, because when I multiply an x squared and an x and 1 more x, I'm going to get an x to the 4. So the degree is 4, so we have an even degree. And the lead term is going to be negative. We can see that negative out in front here. The lead coefficient is negative. So what this gives us, if it's even and it's negative, it's the even tells us that the ends behave much like a parabola. So we're going to the left we're rising and to the right we're rising, or to the left we're falling, to the right we're falling, but they both go the same direction. Because this is negative, it's like a frowning or downward parabola. I'll tell you, the way that I approach the lead coefficient test every time is I say it's either like an x cubed, positive or negative, or it's like an x squared, a parabola, positive or negative. It's always going to fall into one of those categories. This one is like a downward opening parabola, not because of this x squared here, but because its degree is 4. 1, 2, and then 3, 4. So what we'd have is that this is falling to the left and falling to the right also. That's what the lead coefficient test tells us. Let's talk about zeros and jot this down, this definition. You may need to pause the video, but if f is a polynomial function, I pulled this right out of our textbook. If f is a polynomial function, then the values of x for which f of x equals 0. So f of x, that's representing our y, right? The values for which y is 0 are called the zeros of the function. Whatever value, when we set f of x equal to 0, whatever the values of x are that make this statement true, those x's are called zeros. Those values of x are also sometimes called roots or solutions. So when you see the word root, find the roots, find the solutions, find the zeros, it's all same way of saying there's 3 different ways of saying the same thing. Here's how you approach it. You set f of x equal to 0 and solve for x. So when I see this example, if I let f of x equal 0, I'd have 0 equals x cubed plus 2x squared minus x minus 2. This one's going to factor. So I'm going to factor the polynomial. This one I could factor by grouping. So I'll group the first two together. X squared, x plus 2, minus 1, x plus 2. And then that factors x squared minus 1, x plus 2. You remember that factor by grouping? I take the first 2 terms and factor out the common factor. So I took the x cubed plus 2x squared, and their common factor was x squared. When I factored the x squared out, I was left with x plus 2. And then I took the last 2 terms, the negative x minus 2. Their common factor was a negative 1. When I factor out a negative 1, I get x plus 2. And then I take the 2x plus 2's out, and what's left is the x squared minus 1. I'm not quite finished because there we have that difference of squares. I sure hope you've memorized that pattern for the difference of squares. The x squared minus 1 factors to x plus 1, x minus 1. So I have 3 factors, x plus 1, x minus 1, and then x plus 2. And if I set that product equal to 0, I get 3 solutions. This is true when x plus 1 is 0. Subtracting 1 from both sides, I'd get x is the opposite of 1. It's true when x minus 1 is 0. Adding 1 to both sides gives me x equal to 1, and it's true when x plus 2 is 0. Subtracting 2 from both sides gives me x equals negative 2. So the zeros are negative 2, negative 1, and 1. Those are the zeros, or the roots, or the solutions. Let's try this next one. This is even easier because it's already factored for us. So I can take the factors, x minus 3, x plus 6, solve those set those equal to 0, and solve for x. So I'll add 3 to both sides, and I'd get that x equals 3, or when I set the x plus 6 to 0, subtract 6 from both sides, solve for x, and I'd get x equals negative 6. This one asks us to also look at the multiplicity. The multiplicity has to do with the number of times that root is repeated. So this x minus 3 just has a multiplicity of 1. But this x equals negative 6, you see that if I'd written this out like this, let me write it. If I wrote a f of x equals 4, and then here's the x minus 3, But for that x plus 6, I'm going to write it 3 times. For that x plus 6 cubed, it's like x plus 6, x plus 6, x plus 6. So we actually get 1, 2, 3, 4 roots. If we set this to 0, if we let f of x equal 0, we'd get that x could be 3 or negative 6 or negative 6 again or negative 6 again. So rather than actually do this work 3 times, what we're going to say is that x equals negative 6 is a root or a solution with multiplicity, meaning it's repeated, with multiplicity 3. What happens with the graph, by the way, if we have an odd multiplicity and we graph this, then when x equals negative 6, we know that the graph touches this axis, but with an odd multiplicity, what we know is that it actually crosses through. Had it been an even multiplicity, we'd see it touch and bounce back. Let's see what else we can do here. Let's look at the intermediate value theorem for polynomial functions. We can use the intermediate value theorem to say that if f of x is 2x to the fourth minus 4x squared plus 1, that it has a real 0 between negative 1. We can show that this has a real 0 between negative 1 and 0. Here's how you do this. Here's the intermediate value theorem. You know what it's like? And here in the St. Louis region, we're surrounded by rivers. I want you to imagine for a minute that we've got this river. Let's have this be the Missouri River. Separate St. Charles County from St. Louis County. And let's say that there's big walls around St. Louis and St. Charles. So you can pass between St. Louis and St. Charles, but you can't go outside St. Louis and St. Charles together, right? Now you've got someone who's over here in St. Louis County, and they pass over here to St. Charles County, and they tell you, I never crossed the river. If it's illegal to cross a river, and they say, no, I got over here a different way, I never crossed the river, we know that that just can't be true. If there were these giant walls, and let's say that there's no air flight either, right? No air travel. That you can't drive from St. Louis County to St. Charles County unless you go way around the river somehow and come back, right? You've got to, at some point, you've got to cross the river. And that's the intermediate value theorem. Because what we're going to see here is for f of x, when x is negative 1, so let's find f of negative 1. We get 2 times negative 1 to the fourth minus 4 times negative 1 squared plus 1. And if I put a negative 1 in for x, what I get is 2 minus 4 plus 1, because negative 1 to the fourth is just 1, so 2 times 1 is 2. Negative 1 squared is 1, so that's just negative 4 plus 1. So I get a negative number, right? 2 minus 4 plus 1, negative 1. Now find f of 0. So 2 times 0 to the fourth minus 4 times 0 plus 1. If I replace the x with 0, I'd get 0 plus 0 plus 1, positive 1. So here's what we've got going on. When x was negative 1, when x was negative 1, y was down here below the x-axis. When x is 0, y is above the axis. So because I know that this polynomial is continuous, it doesn't have a gap or a break, it keeps going from these 2 points, could curve around a little bit in between there, but I know that it's continuous. There's not a break or a gap from point x equals -1 to the point x equals 0. To get from this negative to the positive, what do I know has to have happened? I know that that graph somewhere has to have crossed the x-axis. So somewhere between this value where y was negative and this point where y is positive. I apologize if you hear my dog coughing in the background. That's what that noise is. But I know that the graph at some point crosses over the axis, that we have a 0. And that's the intermediate value theorem. Well, I'm going to call that the end of this video because we've gone 20-some minutes. And this is the first part of a 2-part video series for this section. In the next video for this section, we're going to look at graphing polynomial function. And so we'll start with looking at turning points, and then we'll move on to actually graphing a function. So I'd give you a suggestion that you review this video, watch it a couple times, and then come back to watch the remaining piece.